and welcome. Graphing floor and ceiling functions. First, let's recall the definition of floor and ceiling functions. A floor function is a function from the set of real numbers to the set of integers, and is denoted this way. You see two small bars underneath here below. That's floor. Floor function at x is the largest integer less or equal than x. While the ceiling function at x, and see the two bars are on top, is a function from the set of real numbers to the set of integers, and it's defined as the smallest integer greater or equal than x. So if x here and on the number line, this integer here will be the floor function at x, and this will be the ceiling function at x. It's more like you're rounding up here and you're rounding down here. So x is sandwiched between the floor function of x and the ceiling function of x. Now, if x here is between two integers, n and n plus 1, then the floor function at x is n, and the ceiling function at x is n plus 1. So now some examples here quickly. So minus 2.8, the floor function at minus 2.8 is minus 3. And the ceiling function at minus 2.8 is minus 2. If I take now this one here, the floor, its floor is 3, and its ceiling is 4. If I take now this one, it's exactly the same as this. The floor of 3.9 is 3, and the ceiling of 3.9 is 4. If you take 1/2 here, 0 is the floor of 1/2, and 1 is the ceiling of 1/2. If you take minus 1/2, the floor is minus 1/2, and the ceiling is 0. If I take 2, it's an integer now, so the floor and the ceiling of 2 is the same as 2. So this is very important that we are going to be using today, is if x is an integer, then the ceiling function at x is equal, the floor function at x is equal to x. Now we're going to have some note here. This interval like this, it's the set of real numbers greater or equal than a and less than b. So it's closed from the left, open from the right, and we use this for it. This one here is open from the left and closed from the right. That's x greater than a and less or equal than b, and we use this. This one is open on both sides, so that's x greater than a and less than b, and we have this here. This is closed from both sides, then x is greater or equal than a, less or equal than b, and we use this for it. Now we're going to see a lot of examples. This example is really the reference function. That's the basic function, the basic floor function. We're going to be drawing this from R to R, and obviously the range of this function is z, is a set of integers. So we make a table. Use this number line, it will help you quite a bit. So we're going to use x between -3 and -2, -2 and -1, up to 3 and 4, always closed on the left and open on the right. So now when x is between -3 and -2, x is here, the floor function is at x is -3. When x is here, -2. When x is here, -1. 0. When x is here between 3 and 4 is 3. So once you have this, now it's easy to draw that. You get the coordinate system. You say between -3 and -2 is -3. Is right here. So close from the left, open from the right. Between -2 and -1 and -2. Between these 2 points here is -2. Between -1 and 0, you get what? You get this. Between 0 and 1, you get 0. Between 1 and 2, you get 1. Between 2 and 3, you get 2. Between 3 and 4, you get 3. And you see that all close on the left hand, and open on the right hand. So x goes from here, it was 0, 0, 0, 0, 0. As soon as it gets to 1, it jumps. It keeps staying at 1, and then at 2, it jumps, and so on and so forth. Now let's see the ceiling function. That's also a base function here. For us, is a function from R to R, and we use the same thing now, except now the intervals here are closed on the right side and open and on the left side. So when x is between -4 and -3 here, not including -4, obviously, the ceiling is -3. And then here, -2, -1, 0, 1, 2. Between 2 and 3, the ceiling is 3. You draw it now again, you take from -4 to -3. The value is -3. It goes down to here. It's open on this side, closed on this side. Then from -3, -2, we get -1. And then here sorry, that was -2, -1, 0, 1, 2. Look, between 2 and 3, between 2 and 3 is 3. Between 2 and 3 is 3. Open on the left side and close on the right side. So here it's all 0. Once it gets all 0, and then when it jumps up, it can jump up to 1, stays 1 here until 1, and then goes up to 2, and so on and so forth. Now, side by side, this is the floor function, and this is the ceiling function. Those are also called step functions. They are discontinuous functions. They are onto, it's onto z, okay? It's onto the set of integers, but not one-to-one functions. Now, let's see how the graph of the function fx is equal to the floor function of 2x. So in all these situations you will see down the road, we're going to call this a w, or different variable name. 2x is w. Then I will compute x. X is w over 2, or half of w. So now you make this table. W is between -3, -1, -2, -1. Now this, we just did that in the previous examples. We did that in the first example. Now we have to find what is the value of x. X is half of w. So this will be -1.5 minus 1. This will be -1 minus 0.5. This will be -0.5, 0, and you continue to fill up this last one, for example, between 1.5 and 2. Now you ignore all w. Now you don't deal with w anymore. You deal with x. So you get the coordinate system when x is between -1, 0.5, and -1. Here it's going by 1/2, 1/2, 1, 1.5, 2, 2.5, -1/2, -1, -1.5. So -1.5 minus 1, between here to these 2 points, it's -3. Between -1 and -0.5, -1, -0.5 here, you get -2. Between 0.5 and 0, -0.5 and 0, you get -1. Between 0 and 0.5, you get 0. Between 0.5 and 1, 0.5 and 1, you get 1. And you continue that. Now, you notice what happened is the floor function at x, the first example we did is compressed by a factor of 2. Is shrunk, is reduced by a factor of 2. Now I'm going to draw fx equal 1/2 of x, 0.5x. Again, you call this w, and then x is 2w. We make this table. Now, every time you see this, pause and solve. You may pause the recording, the video, and solve the problem and come back and check your answer. So here x is equal twice 2w, so that would be -6, -4, -4, -2, and you get all of this here. When you have 3, 4 here, you get 6, 8. 2, 3, you get 4, 6. Now you put the coordinate system, and then you also pause the video and draw this function. So you look at x between -3 and -4, -6 and -4. Between this here, -6 and -4 is -3. Between -4 and -2, -4 and -2 is -2. Between -2 and 0 is -1. Between 0 and 2 is 0. Between 2 and 4 is 1. Between 4 and 6 is 2. This one is not drawn. So here what you notice is the floor function at x, the first example we did, is stretched by a factor of 2. Stretched by a factor of 2. So here, side by side, this is the floor function of x. This is the floor function of 2x. You see how x is compressed by 1/2, by 2, by a factor of 2. And this one here is stretched by a factor of 2. All right? So when this number is greater than 1, you will have a compression. When this number is less than 1, you will have a stretch. Now let's look at this example. If x is the floor function of x plus 2. Again, we call this w. X is w minus 2. And again, you can pause and fill up the table. So we get this table here. We're just subtracting 2 from each one of this. For example, here you subtract 2, you get -5, -4. Here you subtract 2, you get -1, 0. Here you subtract 2, you get 1 and 2. Now we want to draw this. Between -5 and -4 is -3. -5 and -4 is -3 right here. And between -4 and -3 is -2. And you keep going. This is the function. What happened is you see that the original function x, floor function of x, is shifted 2 units to the left. Shifted 2 units to the left. Because this was here, and it shifted to unit 1, 2, shifted 2 units to the left. Now let's see what happened when floor function of x minus 2. We get this is w again. So x is w plus 2. You do the table. So we're adding 2 now to each one of these. And we get this. Now we're going to draw that. So between -1 and 0 is -3. Is here. And then here's -2. -1, 0, 1, 2, 3. So what you notice here is the floor function of x is shifted 2 units to the right. This was here, shifted 2 units to the right. So here's x, floor function of x. That gives me floor function of x minus 2. Shift 2 units to the right. Shift 2 units to the left gives you the floor function of x plus 2. Okay? Now, this one here, fx is equal to x plus 1/2. That means x plus 1/2 is x plus 1/2, the floor function. Now, we would expect that we have a shift of 1/2 unit to the left. 1/2 unit to the left. Let's do that. Again, we call this w. X is w minus 0.5. You do the table. Now we're going to draw that. Okay, so between minus 3.5 and minus 2.5 is minus 3. This is here, it goes by 1, 2, 3, 4, that goes by 1/2. 1/2, 1, 1.5, 2. Minus 1/2, minus 1, minus 1.5, minus 2. So it's going by 1/2. So minus 1.5, minus 3.5, minus 2.5, minus 3, minus 3.5, minus 2.5 is right here. You get this. Between minus 2.5 and minus 1.5, minus 2.5 here, and minus 1.5 here, you get this. Between minus 1.5 and minus 1/2 here, you get this. So what happened here is shift to the left 1/2 unit. See here what happened here. So now here's x minus floor function of x minus 1.5. So again, we do the same thing here. X is equal to w plus 0.5. Again, you can fill up this table. You draw that, you get this now. See, what happened is my floor function at x shifted to the right 1/2 unit, 1/2 unit. So here's the floor function of x. Here is the floor function of x minus 1/2. When this is minus, we are shifting to the right, 1/2 unit. This one here is x plus 1/2 is shift 1/2 unit to the left. Now, this is an interesting example. Let's draw the graph of the function fx equals seeding function of x minus floor function of x. When you have situations like this, you have to distinguish two situations, two cases, when x is integer, when x is not an integer. So when x is an integer, we just mentioned in the beginning that this will be equal to this will be equal to x, you get a 0. Now, when x is not an integer, so x is between n and n plus 1, the seeding function of x is n plus 1. The floor function of x is n. So now you're subtracting n plus 1 minus n, you get 1. So this function here is 0 when x is an integer and 1 if x is not an integer. Now you can draw that. So first, let's do when x is an integer. Say minus 4, you get 0. Minus 3, you get 0. 0, 0. Now, since this is a value of the function, then the function will not have a value on all of these points. All of these points will be open. Now we're going to see between x between -4 and -3, the value of the function is 1. -3 and -2, you get 1, 1. And that is the graph of the function. Seeding function of x minus floor function of x. Very interesting. Here's another example. Fx is equal to the floor function of x times the seeding function of x. Again, you need to distinguish two cases. X is integer and x is not an integer. So when x is an integer, say x is equal to n, this will be n and this will be n, you get n squared. When x now is between n and n plus 1, the floor function is n. The seeding function is n plus 1. You have to times them. So it gets you n squared plus n. N times n plus 1 gets you n squared plus n. So remember, this here, in this case, is the floor function of x. And this here is the seeding function of x. And you are times them together, okay? So now we're going to draw this function. Let's see when x is an integer. Let's see between -3, -2, -1, 0. Let's see that n squared. So what is -3 to the power 2 is 9, 8, 9. -2 gives you what? 4. -1 gives you what? 1, 0. 1, 4, 9. Done with this part of the function. Now we need to see when x is between two integers. So x between these two integers, see? These two integers, then n is -3 here. So -3 times -3 plus 1 is -2, and you get what? 6. Now, when x between -2 and -1, so n is -2, -2, and then here you get -2 plus 1 is -1, -2 times -1 gives you 2. So this is 1, 2, 3, 4. And then you get 0. You continue here between 1 and 2, 1 and 2. So n is 1. 1. 1 plus 1 is 2. 1 times 2 is 2. Look at this one. It's very interesting, very interesting. Okay. Now, let's see floor function of x plus ceiling function of x. So now again, distinguish two cases. When x is equal to n is an integer, this will be n, this will be n, you get a 2n. When x is between n and n plus 1, the floor function is n, the ceiling function is n plus 1, you add them, you get 2n plus 1. So now we have the function defined precisely this way. So I will let you fill up this table. And we get this table. Now we need to draw that. So let's see what happens when x is an integer. So we're starting from -3 here. -3, you get -5, right? -6, no, 2n. Not we're doing 2n now. We are doing 2n, this line here, okay? -3, you get -6. -2, you get -4. -1, you get -2. And then 0. Okay, now I'm done with this part, Now I need to do this part. I have the values here, okay? I have the values here. But now I need to look at the intervals. When x between -3 and -4, I don't have -4 here. When x is between -3 and -2, -3 and -2, so what do you get? -5. When x is between -2 and -1, -2 and -1, so n is -2, you get what? I'm looking at 2n plus 1, you get -3. And then when n is between -1 and 0, 2n plus 1 will be -1, and you keep going, you get this function. Very interesting function. Floor function of x plus ceiling function of x. Now, let's see what happened to this example. Is a ceiling function of x plus ceiling function of x divided by 2. Again, you have to distinguish two cases here, and a lot of there's some more calculation here. So what you need to do, I prepared this table for you. So you have x. I chose these points here. Okay. Then you compute floor function of x. As we know what will be these values here. Okay. It will be exactly the same as this. When you have an integer, those will be the same. Now you compute x over 2, and you find the ceiling function of x over 2. Then you add these two to get fx. And then here is between -6 and -5. Here between -5 and -4. So pause and solve. You get this table. So now we can easily draw the function. You can again pause and draw it. So let's see. Here's my f. When it's -6 is -9 is down here, so we don't see it. Let's start from -5. When x is -5, I get -7 right here. X -4, I get -6. -3, I get -4, okay? -2, I get -3. -1, I get and so on and so forth. We'll keep going. So let's see. 3, I get what? 5. 4, I get 6. Now I'm done with the value when x is these integer values here. Now we are going to look between -6 and -5 is -7. -6, -5, -6 and -5 is -7. Between -5 and -4 is -6. And then -4, keep going. So let's see, between 1 and 2. Between 1 and 2 is 3. Between 2 and 3 is 5. Between 3 and 4 is 6. Very interesting. Now let's draw this function. Fx equals a floor function of 2x plus 1. So I'm going to take 2 outside. It'll be x plus 1/2. We're going to expect here 2 transformation. Because of this plus 1/2, there will be a shift to the left. Because this is a 2, it will be also a compression of a factor of 2. So let's see how that goes here. Again, you call this W. Find x. X is equal to W minus 1/2. Okay, so we make the table. Here's the table. We need to draw the function. Again, take your time. This is going by 1/2. So between -2 and -1.5, here is -3. And then you get, okay, now we know we can do that a little bit quickly because you have used quite a bit of them. So see what happened here is they'll shift half a unit to the left, and there's a compression of a factor of 2. Okay, it's very interesting. Now look at this here. This is 1/2 x minus 3. One would expect a shift 3 unit to the right, and since this less than 1, it will be a stretch of a factor of 2. Again, you do that, you compute x, get that table going. You get this table, and now you need to draw this. So we are going here by 1. 1, 2, 3, 4, 5. Okay. So between -7 and -5, somewhere here is -4. It's right here, and then here. So what happened is we stretched the ceiling function of x 3 times. So the ceiling function of x was here. So 1, 2, 3. Well, this point will not move anymore. It will stop there, but then you stretch the function by a factor of 2. See? Okay, that's interesting. Now let's see the fx is the floor function of square root of x. Now, obviously, x has to be positive here, not negative. Okay, so again, you call this W. So x is equal to W squared. Now you can use this table here. Okay, these are the values. Now we can draw this function. Between 0 and 1, the value is 0. Between 1 and 4, the value is 1. 4 and 9, the value is 2. 9 and 16, the value is 3. It's very interesting. Now, if you remember the function fx equals square root of x is like that. And when x is a real number. So this one is a discrete, okay? It's a discontinuous function. It's it's taking the same shape. So let's look at x squared, floor function of x squared. Anything I'm doing with floor function, you can do with ceiling function. It's the same thing, exactly the same method. So you call it wx equal x squared, then x equal square root of w. Here is the table, I'm giving it to you. Now you have some numbers here that you need to approximate, the square root of 2, square root of 3, maybe use one decimal point. So if you draw it, it looks like this. It's very interesting because the function fx equals x squared looks like that. Okay. So we now let's look at this function. That's another interesting function. X minus floor function of x. Okay, again, you make the table here. Use this number line will help you. These are the intervals I'm going to be using. Since I'm involved here with the floor function, so I need to close it from the left and make it leave it open on the right. So you just calculate that, you get x, you get these values. Now this is a straight line, x plus 4 is a straight line. So now you need to draw this function. So if you're drawing, say, y equals x plus 4, you can take 2 points. If I take negative 4, I get 0. And if I get negative 3 here, I get 1. And then you draw the other one here. Very interesting, very interesting. So now, how can you get the graphs of the following functions from the graph of the function fx equal floor function of x from R to R? Okay, so okay, if you have a floor function of x plus 1, this is a plus, there will be a shift to the left, 1 unit. This is x minus 1, it will be shift 1 unit to the right. 4x, this is greater than 4, it will be what? A compression, a factor of 4. This is x divided by 4. There will be a stretch by a factor of 4. This one will be what? A shift a quarter of a unit to the left. This one here that's 2 transformation here. You have 4 and you have x plus 1/2. So you will have shift half a unit to the right. And since this is 4, you have a compression of a factor of 4. This one here is, since that's divided by 4, so that will be shift 3 unit to the right and stretch by a factor of 4. Now this and all of this, you can do it now really easily. Now, when I'm adding here a number here, when it's an integer, there's another way of doing it, but you can't do it when you have a fraction here is added to the x. So let's see that. What is draw the function fx is equal to 2 times floor function of x. You get the table here. That's the table. You pause and draw it. Okay, that is the twice the floor function of x. See, fx is equal to floor function of 2x. There is a compression of a factor of 2. See, this one here, you are multiplying your function by 2. They are not the same. Exactly, they're not the same. Absolutely not the same. Okay. So now this thing happens. I wanted to notice something here. So this is a floor function of x. Again, the same here. Look what happened now. If I shift the floor function of x 2 units to the right, what do I get? I get this function. We just spoke about it. Look at it again now. I'm going now to shift it down 2 units. So I get the same function. These two functions are the same because you can continue here, see? They are the same. So you can get the same results because when fx is the floor function of x minus 2, this can be taken outside of the floor function. So which means your function x, floor function of x, you dropped it down 2 units, minus 2. And those are the same. Now, again, let's see what happens in shifting to the other direction. See, if I shift x, floor function of x 2 units to the left, what do we get? We get this. Now, if I take this now and shift it up 2 units, I get the same thing. These are the same function again, okay? And I get this works because the floor function of x plus 2 is equal to the floor function of x plus 2. Okay? Now, another note here, fx equal x plus 1/2 of x, floor function is not equal to floor function of x plus 1/2. You cannot get this one outside. It only works when this is an integer. And here's a counter example. Okay, you can make a lot of counter examples. So to get the graph of fx, which is like this, x plus 1/2, from the graph of floor function of x, you must shift to the left the graph by 1/2 unit. Shifting this up 1 unit will not produce the graph of fx equal x plus floor function of x plus 1/2. This is an important property of the floor and ceiling functions. For any real number x and any integer x, the floor function of x plus k is equal to the floor function of x plus k. That's, you can get k outside. And here you can also get 1k outside. And this is not always the case. It will not work if this one is not an integer. Now, for the property of floor functions and ceiling functions, I suggest that you can watch this YouTube about the floor and ceiling functions. And that is all for today. And thank you and goodbye.